So I'm back in NAGRA after almost 2 years away, where I had met actually Ingo. He was a fantastic person, fantastic help for Asclepios I mission. And I don't know, Ingo, if you'd like to introduce yourself in a few words.
Yes, so my name is Ingo Blechschmidt. I'm a geologist by background, and I'm working here at that site since 2004. I started as a site geologist, and after a few years I took over the lead as the site manager. Welcome to Grimsel Test site. So you see here the layout of the facility, and now we are about 450 to 500 meters below surface, and everything you see here in this orange color is related to our facility, so to Grimsel Test site. Grimsel Test site is a pure research facility. We're doing mainly work related to radioactive waste issues in Switzerland, and we also support projects for our international partners, and you see a nice list of countries working with us here. And the idea is that we are doing work in support of the development of concepts for the disposal of radioactive waste in future so-called deep geological repositories. And there are many issues behind which needs to be discussed, which needs to be solved, and in some of the cases needs to be demonstrated under realistic boundary conditions in situ in such an underground research facility. Okay, so we will leave now our central facility. You may have realized that here we have everything we need. We have workshops, we have offices, we have labs to deal with rock samples, and we also have a kitchen, and we also have meeting rooms. So we're leaving this area now to enter the final research tunnels and galleries, where I can show you what we are doing at the moment. So we need to enter this door. So please,
thank you.
Watch the stairs. So the site by itself is owned by NAGRA. NAGRA is an organization in Switzerland which is responsible for dealing with all types of radioactive waste and developing solutions for the final disposal of the radioactive waste. So NAGRA is a non-profit organization, and a lot of our work is related to RD&D, so to research, development and demonstration for the disposal concepts we are developing. And in parallel with this work, NAGRA is also responsible to find a suitable area, a suitable rock formation which can host a future repository in Switzerland. And NAGRA was founded in 1972 already, which means we already have half a century of experience in this area. And and last year we entered, or we achieved a final milestone in our work by proposing our future repository site in northern Switzerland. What you see here is one of our main tunnels in our facility, and you also see the nice round shape, and this is what you get if you excavate such a tunnel using a so-called tunnel boring machine. And if you look at the photographs here, you see the tunnel boring machine we used at the beginning of the 80s, because Grimsel Test site as a research facility was constructed in 1983 to 1984, which also means that the research here is ongoing for almost 40 years. And each of the galleries and tunnels you see here are dedicated to specific research activities. So we have galleries where we focus on large-scale demonstration experiments, where we simulate future disposal concepts and checking if they will also work under realistic boundary conditions. So there you can also see that there is an important link between normal lab studies at the surface, at a research institute, as a university, to the final repository site. So with the work in these underground research labs, we try to meet the kind of missing link between small lab scale experiments and the realistic situation we have in the future repository, with respect to size, but also with respect to time. So while walking through the tunnel, you will also see components of our exhibition, and this exhibition is not prepared for the scientists working here. This exhibition is mainly prepared for the visitors we have, because we also welcome students, we welcome people from any area to see, to watch us, and to understand what we are doing here. And one very important aspect of our work is time. Because for our disposal projects, we need to oversee a time span of a few 100,000 of years, because we need to guarantee that the radioactive waste is isolated from the surface, mainly from the biosphere, from the people, for at least 1 million years. And this is also the reason why so many geoscientists, geologists working in our area. Because as you know, geologists, they're kind of historical people. Everything they know, they know from the history, you know, from everything which happened on Earth in the past. So we're taking the situation we have on the Earth, we're trying to understand under what boundary condition the specific rock type was formed, how it developed with time, and then we compare it with the current, with the recent situation. And with these two end members, we are able to make a prediction to the future. This is a little bit about the way we work and the way which gives us the opportunity, you know, to make these long-term predictions about the safety and performance of a future repository site.
Ingo, the fortune teller.
What? So, yes, and here you see, as an example, you see a kind of timeline representing the time span or the age of the rock around us. So we have the crystalline rock of the so-called R massif in the Swiss Alps here. And interestingly, this rock is already 300 million years old. And if you have a closer look at the rock, you will see that, yeah, there's not much disturbance. There's not much, there doesn't happen much we disturb the rock during this time period. It's still very intact. So that means in the last 300 million years, in this rock formation there was a certain stability with respect to tectonic stability, but also respect to any other impact, let's say by erosion from the surface or other processes which could somehow disturb the rock properties. So, and then while walking along this line, you know, we're passing the last 300 million years, and they're all the various geological periods we all know about. You know, we know about the time when the dinosaurs disappeared on Earth, and we also know about the time when the first hominids, the first humans appeared on Earth. And that's a rather long time span, and we see that especially at the surface of the Earth, a lot of things happened. But also if you look at subsurface, we know that during these 300 million years, the Earth also developed strongly. So now the situation has changed. Now we are in one of the big caverns we have in Grimsel. This cavern was not dismantled or excavated by a tunnel boring machine. This was excavated by drill and blast. So, and this is a methodology, this is different to using a tunnel boring machine, because the effect on the rock is more strong, so that you also can see that the surface of the rock here appears quite more rough. And this also needs to be considered if you think about future disposal concepts. You know? How much will the rock be influenced by the excavation methodology you're using? Because finally, the rock we select for a future disposal site needs to act as one, if not the most important barrier system. That's why we are spending so much time to selecting a suitable rock formation which can host a repository for such a long time. And there are specific boundary conditions this rock needs to meet. So it needs to be stable for a long time. It needs to be tight with respect to water flow, and it should also have the capacity to retard, to take up radionuclides in case they get released from the waste packages. So if we look at that side of this pattern there, we have a model in 1-to-1 scale simulating the disposal concept for high-level waste. High-level waste means for spent nuclear fuel, which still generates heat in the system as soon as it gets disposed of. So to dispose of this high-level waste, we need to develop a so-called multiple barrier system. Multiple means that we have on one hand side, we have so-called engineered barrier system, which is made of the canister itself, so the disposal canister, and material which is surrounding. And in our concept, we're using as backfilling material around this disposal canister, so-called bentonite. Bentonite material is also a natural product which has a high content of swelling clays. So, and with these properties, or with this, with this material which has this high content of swelling clays, we can create a situation around the disposal canister which reacts at any place similar to any effect, to any change in the system around the canister itself. That sounds very complicated.
It's not. It's very clear.
I will explain it again over there.
Okay.
So I was explaining a little bit about this multiple barrier concept. So we started with the engineered barrier made of the disposal canister, which hosts the waste itself, and embedded in the so-called bentonite buffer. Bentonite made of a high content of swelling clays. It will be disposed of or placed in with a defined dry density, so it has still a certain swelling capacity as soon as it gets in contact with the water coming from the geosphere, from the so-called host rock around the disposal gallery. So, and this brings me to the second barrier of our multiple barrier concept, and that's the so-called natural barrier made of the rock itself. So the rock should have similar properties as the engineered barrier system itself, but maybe more longer lasting. Can I say it in English now?
Yes, more longer lasting. But actually, so do you adapt the bentonite, or do you first select the rock and then adapt the bentonite?
It goes a little bit in parallel, I would say. But of course, we have general understanding that we need engineered barrier system because we also need to transport the waste. So that's why we need a canister also to bring the waste from encapsulation facilities or from an interim storage facility to the final disposal place. So there's certain stability and longevity required. And then, of course, it needs to be embedded in a material which has properties which can protect the waste canister for a certain time. And that's mainly the time the system needs to get back in equilibrium. So the time which the system needs to get back in equilibrium. And then you also need to understand that as soon you construct a disposal facility, you will disturb the entire environment. So you need to construct something, the stress and the rock stress will change, although the water stress or the water pressure in the system will change because you need to pump out the water because people need to work there. So the system will be disturbed from a mechanical point of view, but also from a geo-hydraulical or hydraulic point of view. So, and this disturbance, will change again after the disposal site will be closed after the operational phase. So the water will come back, system will resaturate, and also the stress in the system will get to the previous boundary conditions. And this is very important because for our long-term safety calculations, we're using the undisturbed rock we select. Because this is the situation the system will stand longest. But this also means that we need to guarantee that as soon the disposal facility stops operation and we close it up again, that the system can get back to the previous situation, so get back to equilibrium.
What kind of sensors do you use for that? What kind of measurements do you then perform to measure that?
So we do any type of geological characterization of the rock before we start to construct the facility, because we really get a good understanding of the rock formation we select. So on one hand side, we need to understand the regional geology. What's the water table saying? How many aquifers we have in the system? What is the mechanical stress in the rock at the disposal level of the facility? Because the repository site will be a few hundred meters below surface, because we need to protect the repository for a defined time period for any processes at the surface. For example, river erosion, future glaciation phases. We also need to avoid major tectonic structures. We could also have an impact on the integrity of a repository site. So all these things needs to be understood in a way that we can make prediction to the future, that we can oversee these at least 1 million year we need to cover for the high level waste. So that's why we're doing all these studies and spending so much effort to select suitable rock formations in Switzerland. But this also counts for any other country in the world where they are using, for example, nuclear power for power production, and where they need to find a solution for their radioactive waste. Yeah. So in case the engineered barriers will lose its function as a barrier, for example, when the metal disposal canisters will corrode, then the natural barrier will take over the barrier function for the long term. So the experiments we are doing here at Grimsel Test site in these research facilities are exactly related to the various or different components of the multiple barrier system we have. Which means we have experiments where we are looking for the behavior of different canister materials under realistic boundary conditions in the geosphere. To understand under which or what conditions, for example, this canister start to corrode, and how long it will take to get or to observe a failure of these disposal canisters in a realistic, under realistic boundary conditions. And then you also look at the buffer material, the bentonite material around the disposal canister. Because when the canister might fail, some of the radionuclides might get released to the buffer material. And then, for that reason, we need to understand under what boundary conditions radionuclides stay mobile in this buffer material. How get they transported, if they get transported at all, through this buffer material? And how long it would take that radionuclides released from the canister will reach the geosphere. So, if experiments looking at the canister, if experiments looking at the processes in the interface between the canister and the bentonite material, then we have experiments where we're looking only on radionuclide behavior or mobility in the bentonite material. But then, of course, we also need to look at the interface between the rock and the bentonite, because this is a highly active area, because pore water from the bentonite will meet pore water of the rock. So there are two completely different water chemistries, which means the system is highly disturbed here. So there we need to understand what the impact of this disturbance will be on radionuclide mobility. Will the radionuclide mobility here be increased or decreased? And then, of course, we would like to understand how and if radionuclides get transported into the rock itself, and how these radionuclides get trapped in the rock, because the rock is our main barrier. Yeah, over here, what you see here, you see blocks of bentonite. So that's the way how we receive bentonite, in blocks or sometimes in granular form, depending on what type of buffer material you would like to study. And then if you look here, this is a large diameter core drilled in the crystalline rock, in the granodiorite here at Grimsel. And there you see that it's very important that we are able to look into the rock, to drill boreholes, to test in situ, that we really understand how the rock, but also the buffer materials we bring in on the realistic natural boundary conditions. And sometimes, if we have luck, we meet in our borehole open fracture, nice tension fractures with nicely formed crystals. And as we are in a granitic type of rock, the main crystal we see here is the so-called quartz. Quartz crystals, very nicely seen here.
So we're getting a shower right now?
Yeah.
Nice.
So, water. Maybe you can hear that we have water flow. Water is dripping in this small cavern here. And this is something very typical for a crystalline type of rock, like this granodiorite, because we have fractures. And in these fractures we have water flow, active water flow. And this is the big difference to other potential host rocks for geological disposal, like the clay type of rock, like the Valinus clay in northern Switzerland. Which means at a site where we have a crystalline type of rock as a host rock, we need to deal with the water in the fractures. We need to deal with water flow in our disposal concept. And this is something we also study here at Grimsel, but mainly for our international partners around the world, which are interested in crystalline rock as a potential host rock for a future repository. So for studying, or for understanding the host rock, or the rock we selected, we normally need to do a lot of boreholes that get really an understanding of the rock behavior on the realistic in situ conditions. This with respect to in situ stress, because we have, as I said before, we have a few hundred meters rock above us, so there's a certain load on the rock. And then the rock is also saturated. The whole rock is full of water. So, which means, as soon as we drill a borehole, the borehole will fill up with the water from the rock formation. And then, by sealing up the boreholes with this so-called packer systems, the installations you see here to seal up the borehole, we can collect the water in the borehole and also can measure the pressure which is building up by sealing up the borehole. And this gives us direct information about the hydrostatic pressure we have in the rock formation. And all these manometers, they provide us the data about the various pressures in the intervals we are monitoring in the rock formation. This is a special device, a special saw we developed to take samples from rock samples which got in contact with radioactive materials. Because one of the specialities we have here at Grimsel Test site is that we have the ability to use radionuclides in our in situ experiments. So we can really study under realistic boundary conditions how radionuclides, in very low concentrations of course, get transported in the rock under the specific boundary conditions we have. Transport via fractures or transport by using the available pore space by diffusion in the granite rock.
Was it?
I will explain to you in a minute. So, yeah, this is a small demonstration experiment. I would say it's maybe the most simple experiment we have here at Grimsel Test site. But it is at the same time also very impressive. Because it simulates or it shows the behavior of bentonite material on the left side, dry bentonite, in a form which it will be placed in a disposal site. And then on the right side, in the right column, you see the same amount of bentonite which got in contact with about 2 liters of water. And there you see how the bentonite behaves as soon as it gets in contact with water. It's changing its volume. Volume is increasing dramatically. And also something very important is that also the granular structure of the bentonite is disappearing. So the bentonite appears now as very homogeneous. So it's sealing up by increasing the volume and also by closing all the gaps between the particles or the grains we had before. And this is a very important behavior because this will really isolate the disposal canisters and the disposal galleries. You know, how does microbial activity impact, for example, canister corrosion?
Does it influence any of the radionuclide transport?
Not directly as I know, but we are more concerned about the impact on the barriers, mainly on corrosion activities of the canister materials we use.
Very impressive.
And of course, you know, if you have microbial activity, then you also need to deal with gas generation in the system.
And that can cause more stresses and explosions.
Yeah, exactly. And if you reach critical gas pressures in the system, so if the gas pressure is exceeding the pressure, the hydrostatic pressure in the system, the gas wants to get released. And the release of the gas can cause preferential flow paths for contaminated water, for example. That's why we need to deal with the gas. We cannot avoid, but we need to understand where we need to expect gas. Then we need to understand what gas generation we have. It also depends on the waste form. It also depends on the canister material, because if you have a carbon steel canister, and when it corrodes, you might get hydrogen as gas.
Hydrogen brittlement then of the steel, yeah.
Exactly.
Yeah.
So, or if you have organic waste materials like bituminous waste, which in former times waste got embedded in bituminous materials, and then you can get methane, for example. So, as we can't avoid gas to be generated, we need to design the engineered barrier system that gas can be released in a controlled way.
So you have valves, or you have some tubes?
No.
What do you have?
That's also one principal concept, that these disposal concepts, they should be very simple in their design, because they need to function without any interference of humans afterwards. This is what we call passive safety, because as soon the repository will be closed after about 100 years of operation, the concept should work by itself. Nature will take over.
You're saying you're not going to be here in 100 years to take care of all of this?
I will try. But yeah, let's see.
Hoppala.
Yeah, let's walk a little bit to the north, and I wonder if you will realize any change in geology while walking this gallery.
Get around, boys and girls, we have a quiz today on geology. So how deep is that tunnel?
How deep?
Yep.
Here we are about 450 meters below surface, and it's not so easy it's not possible to say that the lab is exactly 500 meters below surface, because we are in the Swiss Alps, where we have a rather strong topography, and depending where you are, the system, it's maybe only 420 meters, and if you're getting deeper, then it's overload, so the overburden is maybe about 500 meters. That's why I'm always saying, we are around 450 to 500 meters below surface. So now you see the rock is getting darker. So we're coming now from the so-called essential art granite. That's this more light-colored rock, and maybe I can also switch off a light. Switch on the light.
That'd be very useful. Thank you. So this is where we're going, and this is where we came from.
Yeah, that's the granite. You see it on the more light color, and if you move to here, there you see that the color of the rock is changing, and this is already the first sign that also the rock type is changing. Now we're coming from a granite, and now we have this dark colored, sometimes greenish, also appears a little bit more sheared, a little bit more deformed rock, which is a lamprifier. That's a rock formation which is about 20 million years younger than the granitic rock around, so it's about 280 million years. And this intruded at a later stage, at a time when the granitic formation was already cooled down in a way that this more mafic magmas, these rocks from the deeper levels of the crust could intrude into this crystalline rock body. And then it got stuck. Now this is a very important geological feature in our system. Because this is a so-called area where the rock will break first. Because there the rock properties are so different. So both rock types will handle the stress in a different way. At a time when the granitic rock will already break in a more brittle way, the lamprophile with a higher content of clay minerals or biotite will still act in a more ductile way. So you also see a few faults in the system, and this is very important to know, because this also means that in the interface between these two rock types, you also might get secondary mineralization or deformation of the rock, which will also change the properties of the rock for water flow. So maybe the permeability is changing. That means if you have these geological features in your host rock of a repository, these might be the highways for water flow, which you need to understand, and where you need to find solutions to deal with.
What's that?
This is a device which is placed at an area where we have a tectonic feature. It's a lamprophile which shows a strong tectonic overprint, and this is a device measuring the movement between two rock blocks. It has not the resolution like a seismometer, let's say it like this. It's a different concept here.
I think the rock is absolutely fascinating. Like,
You studied the wrong one.
this is very like crystalline, and this one is like,
Yeah, this is more like a clay, more fine-grained. That's why you see all this cleavage, shearing here, because it's reacting against stress differently than the more massive granitic rock.
mm-hmm.
Which means here the stress can reorientate minerals more easy than in this more rigid, very hard granitic rock.
So what am I seeing here?
Yeah, this is an experiment where we are looking on bentonite behavior in a borehole. So this is a borehole which is about 20 meters long, and if I remember correctly, after 4 or 5 meters we have bentonite rings. Yeah, again, this is a packer system which we use to seal up boreholes, and at this packer system we have bentonite rings in place at an area where a tectonic feature, a fracture, is intersecting this packer system at about 5 to 6 meters from here. So, and there we're studying the saturation behavior of the bentonite. Maybe you remember that we're using prefabricated bentonite blocks with a defined dry density to get a certain swelling capacity of this bentonite material as soon as it gets in contact with the water. So now the bentonite in the borehole is taking up all the water coming from the rock and from these fractures, from these water conducting features, and saturating and generating a swelling pressure in the system, sealing up the borehole. But what is more interesting here is it might also release bentonite particles to the fracture, because here we would like to understand the erosion behavior of the bentonite. Because if you have fracture in a rock and if you have advective water flow, you need to consider mass loss of your buffer system. Of course, only talking about 1, 2, 3, 4 years, it doesn't mean much. But if you go into the long-term perspective, if you need to see 10,000, 100,000 years, you know, a few particles per day, a few milligram loss of bentonite a day can mean a lot. So here we have all the devices to monitor the experiment, to measure the water pressure in the borehole, to measure the swelling pressure of the bentonite, and also you see also the lines which form the connection to our data acquisition system, and you also see lines to our on-site chemical cabinet, because we're also measuring change in water chemistry, EH and pH, and we're also measuring turbidity in the outflow, because turbidity is also a sign of release of bentonite particles in the system. All our experiments, they are connected to our internet, and our researchers, they always have access to the data from outside. So no one needs to be around the whole day. New boreholes in northern Switzerland, we construct or start the planning of the shaft to get access to the repository site. That would be a huge, it's a century project, how we call it. It's also written on our website, century project, we're working for a century. Yeah, so we always have these nice posters explaining about the experiments. We have one big demonstration experiment ongoing at the moment. It's a so-called high temperature effects on bentonite buffers. And this is again one of the experiments where we testing an entire disposal concept. There we are not only looking. What do you mean?
Speak louder. Sorry.
Louder.
Yes, I'm sorry.
My voice
no,
is.
just because of the cars.
I will start again.
Sorry. Go ahead.
Yeah, for all our experiments, we have posters explaining to our visitors what are the main objectives of the projects we are running. This is a poster related to one of our big demonstration experiments, the so-called high temperature effects on bentonite buffers. It is a large-scale, 1-to-1 scale demonstration experiment demonstrating the disposal of high-level waste in a horizontal disposal gallery. And high-level waste, when it gets disposed of, is still generating a certain temperature. So in most of the concepts so far, we used about 100 centigrade as the temperature at disposal time, because as known, high-level waste, when it's get out of the nuclear power plant, needs to be stored for a few decades to cool down. And then only then we can dispose of it.
Can you tell me about the instrumentation?
I will, yeah, let me start again. So as we are not allowed to use in our experiments real waste, we're simulating the temperature coming from the waste when it gets disposed of by using large heaters. And in this experiment we have 4 heaters emplaced in 2 different bentonite types, because we also need to understand how different bentonite materials behave. How does the heat coming from the disposal canister or from the waste impact the saturation behavior of the bentonite material? And this, or we need to simulate in large-scale experiments that the heat coming from the bentonite will not have a negative impact on the buffer, on the bentonite performance, which means we want to have a bentonite which gets saturated in a homogeneous way without generating any stress in the system, which could, for example, cause any displacement of the waste drums or even destroy them. And we also need to understand if the heat coming from the waste has an influence on the bentonite properties in the way that we would have secondary mineralization, which could also cause a performance change of the bentonite. that it will have an impact, for example, on swelling capacity or radionuclide degradation, things like that. So, and there you also see that as any of our experiments, instrumentation, monitoring, collecting of data is key. But this is also very challenging for us, because with each sensor for measuring pressures, temperatures, stress, and whatever you need to measure, can have a negative impact on the performance of the barrier system, because you have a lot of lines, a lot of cables, which could also act as pathways for water flow in the system.
So what are some of the essential sensors that you have? What are the most essential sensors that you have, or the minimum measurements that you would have?
So for this experiment, it is very important to get a good understanding about temperature distribution of the system. Of course, the highest temperature we have close to the heater, and then temperature is decreasing as getting closer to the tunnel wall. And of course, we're also interested in how much temperature, or how the temperature will be really in the interface between the buffer material and the rock. But we're also interested in how homogeneous this temperature development is in the system. But also very important is to get a good understanding about the water content in the bentonite. So we have hundreds of sensors only measuring the water content in the bentonite material, but also in the rock around, especially in the interface. Because the water is coming from the rock, and saturation starts always from the rock, and then we're very interested in how homogeneous saturation of the bentonite will take place.
So this tunnel, I think I remember.
Sorry?
This tunnel, I think I remember.
Yeah, you should remember this one. Yeah, you should remember.
What a beauty it is.
Should I say something?
Yes.
So now we are in the so-called north portal of the site. So this is the only entrance to our facility where we can use a car to get in if we need to transport heavy materials or equipment. And what you see here, this is the main access tunnel to a local hydro-powerplant, because we're using the same infrastructure to get to our site as they used to get their facility. So this is a good synergy for us. So we're sharing the entrance and also the costs.
Always useful.
And close to the northern entrance we have this big demonstration experiment located, which I explained before. This high temperature bentonite demonstration experiment, so-called hot bend, that's the abbreviation. And the machinery you see over here was used to bring in the bentonite material, to get it placed around the heater in a homogeneous way. So this is very important for all these experiments, that you have a good control about the material you bring in, because, for example, the emplacement density of the bentonite material around the heater will have also an impact on the saturation behavior and so on.
How deep is the tunnel that it goes into? Yeah. So it's on two rails, I see.
Yeah, this tunnel is about 75 meter long, and about 35 meter at the end of this tunnel we have this large scale demonstration experiment with these 4 heat elements.
Oh, we get in.
Yeah, sure.
Fantastic.
So the main installation phase of this experiment, which is located behind a 2-meter thick concrete block, took place in 2020 and 2021. So we had a really tough time during COVID pandemic because it was exactly the time where we had a lot of work going on here. So, and we are still doing some final preparation, but the heating phase already started. And we already reached target temperatures in the heaters. Then you see all the devices to control and monitor the experiment. And as you see here, 3 of the heaters are heated up to 175 centigrade and one's heated up to 200 centigrade. And this is a very important experiment when it comes to the discussion about optimization of disposal concepts. Because in former times we mainly considered disposal temperatures of high-level waste of about 100 centigrade. So now if we can show that we can dispose of waste also with really higher temperatures up to 200 centigrade, without changing the performance of our buffer material, this provides good opportunity that we can save time and money for the final disposal, because this could have an impact on the footprint of a repository, because then we could dispose of the disposal canister in a more dense way, closer to each other, because the thermal gradient would not have an impact. Or we could also decrease the interim storage of the waste at the surface, which could also save a lot of time and money. So, if we can show that disposing of the waste with higher temperatures has not an impact on the safety performance, this is a good opportunity to optimize the disposal concepts.
What you doing in here?
Wo hast du deinen Laptop?
Ja, das sieht ja keiner. Das sieht ja keiner, dass alles aus ist.
So focused. So what's your day-to-day looking like? Obviously you're not sitting at a desk all the time.
Yeah. I need to think about what to say. Because 99% I'm sitting at the desk. That's why I'm wondering how interesting it will be.
It doesn't have to be interesting. I mean, a job is not always interesting.
Not a nice picture behind us.
What's your exact role here?
So I'm the head of Grimsel Test site, which means I'm responsible for anything related to budget, manpower, scientific program, coordination of international partners, and also developing projects which meet the requirements of the RD&D programs from our international partners and from NAGRA. So now my voice is getting away.
There you go.
So now we're getting closer to the south of our facility, and at that part of our site we have the so-called radio protection control zone. And the radio protection control zone, this is an area where we are allowed to use radioactive tracers for in situ experiment to study the mobility of radionuclides in the geosphere. And this is very important work, especially for the programs where they have a crystalline type of rock, which is a fractured rock of type, selected as a future host rock for repository. Because there, in this environment, they need to deal with the fractures, and they need to understand how much these fractures can contribute to the mobility of radionuclides when they might get released after the failure of engineered barrier systems.
Deep in thought.
So we have experiments here at this gallery where we're looking for radionuclide transport in fractures, but we are also interested in the radionuclide transport into the rock matrix, because we also like to understand under which circumstances the rock itself, the crystalline rock, can act as a barrier by taking up the radionuclides in the rock. Yeah, this is a radio protection control zone based on IAEA regulations, and it can be operated as a level C or B. And based on the level we are working, we have to follow specific safety regulations.
Does walking around with a camera handheld count? Is that safe enough?
Yeah. So we have no open radioactive resources. All the radioactivity we have in the experiment at the moment, they are injected in boreholes into the rock massive. So there is no risk of getting any radioactive contamination at the surface. And also the concentrations of the radioactive traces are very low. Normally the radioactivity we get from the surrounding rock is higher. So this is the setup of a former experiment we did where we were looking for radionuclide diffusion into the rock matrix. This is not active anymore, so we already dismantled the experiment. This is a classical glove box for sampling, and the reason why we have it is not for radio protection issues. This is more about to protect the samples we take for contamination from the air, because we're also looking for colloids in the water, in the formation water, because colloids are small particles in the water, and when radionuclides get released, some of the radionuclides, they like to get sorbed, like to get attached to these colloids. And then the mobility can be changed of the radionuclides with this binding. And to get a realistic understanding about colloid generation and colloid concentration in the water of the fractures, we need to sample these colloids or these water samples with the colloids in a controlled way, that we are not getting a contamination from the aerosols from the air. This is a setup we implemented to get a better control about the flow field in one of our fractures. In one of our fractures we are using for radionuclide migration experiments. And as we want to simulate as much as possible the situation we expect in the future close repository site, we also need to simulate somehow the backfilling of the disposal galleries and full saturation of the entire system. As soon you have an open installation like this tunnel, all the flow in the near field, the nearby rock in the fractures, is heavily disturbed and controlled by this opening, because we have a hydrostatic pressure a few tens of meters away from here of about 40 bar. Here we have almost atmospheric pressure, so the water will all flow into the gallery here, and it's also speeded up by this huge gradient. And to influence this impact, to lower down this gradient, to decrease this gradient, we have this huge installation here simulating the backfilling and the resaturation of the entire system. Yeah, this is the famous crystal cave at Gasteneck, here at the Grimselpass road. This cave, this alpine tension fracture, how we call it, was found when KWO, the local hydropower plant, constructed the main access tunnel to the power plants Grimsel I and Grimsel II. It is also operated by KWO, and we are happy that we are allowed to show this crystal cave to our guests as well. So what do you see? You see all these nice big crystals, whitish and transparent, and this is mainly the quartz. This is the main mineral you can find here as nice crystals formed, and this is exactly also the mineral which forms the main component of the granite around. So that's the granite itself. It's also the source for the minerals which got formed a few million years ago here in this opening. And the nice thing is that the fracture itself could open wide enough that the crystal had enough space to get form in this in its real crystal system.